Okay, so we are now recording the first lecture on chapter 5. And what I've done here is I've prepared one Word document that I'm going to populate as I present the lecture. I would normally just follow the lecture notes for this one. That is, I would open the L5 Word document and go step by step. But I've decided, because of the unusual delivery, I've decided to flip it around. That is, start with some of the end results of some of the derivation and use that as a starting point for the discussion on the explanation for the background theory and anything that is essential to these lectures. That is, to cover the material, I should say, simply. Right, so where did we leave it off last time? Chapter 4 was an introduction to force convection over flat surfaces, but not only flat surfaces. We started looking at the boundary layer equation for curved surfaces, and we restricted those discussion to the special case of mild curvature. In the presence of mild curvature, you end up with an X momentum conservation equation, which generally gives the constraints on velocity and pressure. And that equation, I'm just going to simplify it there. That's a direct copy from the lecture notes. That equation gave a term. I'll remove the other one as well there. Give a term which involved pressure gradients along the X direction. That is, if you have a surface like the flat surface we see here, you potentially, depending on what's downstream, you may have a pressure gradient along the X direction. Okay, but that requires some obstacle or some changes in the surface that will generate a higher, or will change the pressure at some point. And therefore, if you have a higher pressure in one region, you have to have a pressure gradient to get to that higher pressure. If the surface is truly flat, you may remember that we know that the pressure doesn't change as a function of y. That's one of the results of the derivation of the boundary layer equation. Pressure is constant along an axis which is perpendicular to the plates. And we also find that the pressure, no matter where you position yourself, is not going to change as a function of x. That's for the very special case of a flat surface with an external flow. It is a flow which is undisturbed upstream of the plate and which is unaffected by the plate outside of the boundary layer, which is shown here. So if you move sufficiently far from the plate, you have what is called the boundary layer. Oh, sorry, you've got the free stream fluid flow, and that free stream is unaffected by the plate. If that's what you have, flat surface, external flow means essentially a flow which is unaffected by the plate if you move sufficiently far away. So external flat surface flow, then the pressure gradient term goes to 0. If you have any curvature, that pressure term will not disappear. If you have another surface on top here, let's say you are between two parallel channels and the boundary layers from both plates have merged, then that pressure gradient will exist. It's not possible anymore to say that there is no pressure gradient. For that particular case of a flat surface, then we can simplify the governing equation: mass conservation, momentum conservation for an incompressible fluid, energy conservation for that incompressible fluid. It's very easy to work with this. Okay, so we're making progress. We know the governing equation for that particular flow, and we did some analytical assessment of the implication of that. And one of the things we came up with was a formula or functional description of the way the coefficient of friction depends on position and flow properties. Okay, so that's the equation we worked with, or that we ended up finding out. And if you look at the formula sheets that you have available to you on the loop side, you see that we have one equation for this coefficient of friction as a function of x. And you note perhaps the different notation there. So the difference is that in the notes we had exactly what's on the screen here, a formula sheet which comes straight from the reference book. They added the x here as a subscript. Okay. And that's simply there to mean that we use the x position as the characteristic length in the determination of the Reynolds number, and the coefficient of friction is a local value rather than an averaged value. So the local coefficient of friction we find from this table here is equal to 0.664 Reynolds x minus 1 and 2. Okay, I'm just going to remove the borders. Okay, so that's the progression. Okay, so we have the governing equation. From that we know the functional description, and then there is a way to get from there to there that I want to discuss now. What I mean by there to there is just this. Okay, so where does that come from? How did we get this? There is a method which is fully described in the lecture 4, and that we're going to go over fairly briefly in order to understand a little bit more about the origin of this. So there are actually two solutions. So one thing I'll show now is if you look at the lecture 4, and I told you, or lecture 5, sorry, I told you I'm skipping. We have on page 7 of this, these final results there. Actually, here we are. So on page 7, you'll find that we have a description or a list of equations that determines the way the boundary layer thickness, the coefficient of friction, actually just to be consistent with the notation, coefficient of friction, the Nusselt number, and the thermal boundary layer vary as a function of the Reynolds number and the Prandtl number. And if you look at these, they are actually the same. Actually, this is for summary of the integral equation. Okay, so I'll move now to page, there's another one, which is on page, the following page, a little bit more. Exact analytical solution. So that's the difference between these two. One is an actual approximation, and this one is the exact solution. Okay, exact analytical means derived from exact equation, and in fact it's derived from the governing equation. So the way these solutions are obtained is from the exact. You can then average over the length of the plate, and you get average. If you want over the length of the plate, it's all the way to x equal L. If you want it just to in x position, you use the x definition. So we'll talk about these averages later. So this would be to the end of the plate at position x equal L. So obviously the averaging changes the solution. You see that straight away. And in fact, what's clear is that all you do is you multiply the coefficient there by 2. That's what gives you the average there. There's a good reason for that. It comes from the process of averaging that gives us that multiplication by 2. Okay, so there's it's not a surprise. It can be proven and shown. So we have two methods, the integral one and the exact analytical one. The integral one is fully described in the lecture notes. And the exact analytical one, you're just told how to get there, and then you're given the final results. There are constraints applied to these solutions. That is, the solutions are not always valid. They are suitable provided that you have a uniform wall temperature and provided that the flow is laminar. So let's go back a little bit there to the sketch. Uniform wall temperature means the temperature of the plate is the same everywhere. This would influence the rate of heat transfer, and it would influence, therefore, the Nusselt number, which is defined as a non-dimensional form of the convection coefficient H. Okay, so H is a measure of how effective the flow is at transferring heat away from the surface. So it's clear that it will be dependent on the thermal condition. In that case, we're told temperature is uniform. Laminar flow means that you can assume, you can make certain simplification when deriving the solution to the governing equation. For example, here, you don't see any time derivative term. A turbulent flow will involve loads of fluctuations which vary hugely in terms of their scales. And they happen at large scale, perhaps millimeter, centimeter, meter, and they go down to the microscales and smaller. They also change over time. So one fluctuation may take about 10 seconds to evolve, whereas another one may take a microsecond to evolve. So it's quite challenging. It means you need to get a solution which captures that transient behavior. So if you start your solution process from steady solution like these, then it means that you cannot actually apply it to a turbulent flow. Okay, there are other simplifications in the derivation of the solution, which makes it a little bit more complex. So essentially, these solutions are derived from the governing equations that are provided here, have to assume that you don't have a turbulent flow, and that means you have a laminar flow. Right, so that's really what these set of lectures are about. Up to page 8, it's all about explaining the origin of the laminar solution, and in particular those integrated terms that we have now, delta, CF, NU, and delta. I should say they're not all integrated, they are local values. So this one, for example, notation varies hugely depending on where you're looking for, you're looking at which book, which reference book, lecture notes, and so on. So don't be phased when you see difference in notation. Delta is understood to be the boundary layer thickness. You know that it's a thickness that evolves with position. Therefore, you know it's a function of X. You can make it explicitly obvious by putting the subscript X, or you could write it simply by putting the bracket, say that delta is a function of X. Or you can just put delta and know that it is a function of X, and it's actually quite obvious there. It's right there. And the other thing is, sometime you will see it's directly shown there for the Reynolds number as well, but it's not necessary. So what's the Reynolds number? It obviously appears everywhere. Reynolds number. If the characteristic length is X, then it means you use it as the length in the definition of the Reynolds number. You have mu, you have rho, the density of the fluid, and you've got the characteristic velocity of your flow. Okay, so this is the Reynolds number where you've used X as the characteristic length. And U is again written differently. So if we stick to what we have here, it should be written U infinite. We always use the free stream. Okay, so let's be consistent. That's it defined there. All the terms are presented and used. So how do we get the integral form? It's described in details in the lecture notes, so I'm not going to redo that. I'll just highlight the procedure. So integral solution derivation of, okay, as an example. So it's not the full derivation, just an outline of it. You start from the governing equations, the one that are shown here, okay? But you modify them. And to modify them is you integrate the governing equations over y from y equals 0 to y equal delta. Okay, so what does that mean? If we go back here, you're going to apply an integral, a line integral, so a surface integral in 2D if we assume a depth of 1, starting from here and going all the way to here. We'll apply it to this equation and to this equation. So in practice, what it means, you simply put your integral where you put each term, dy, and you go from 0 to delta. Okay, so you do the same for the next one, and then you integrate also on the right-hand side. Okay, so you both integrate left and right. You do the same down here. So these are called the integral form of the governing equation. You start from the same point, but you actually said that you satisfy the governing equation only on average over the height of that domain along the y direction. That is, on average, over the depth of the boundary layer. Remember, delta is the height of the boundary layer. So we make quite a significant change. We no longer are going to satisfy the governing equation exactly, but on average over the thickness of the boundary layer. The next step from there, if you actually apply that, you will find that it gives you these two equations instead of the original one. So if you expand on this and you use integration by parts and you use every trick in the book in order to simplify, you'll see that it gives you a condition on the velocity at the edge of the boundary layer. So how do you read this? The velocity in the y direction at the upper edge of the boundary layer, that is at y equal delta, is going to be equal to the integral of du over dx. Okay, so essentially the integral of du over dx is the integral of the velocity deficits. That is, how does velocity changes as you move from u along the x direction. So how would you look at it? U changes as you go from there to there. Okay, it comes from the growth of the boundary layer. And that change, so if you look at the amount of fluid that flows through here and the amount of fluid that flows through here, you'll have to have, or if the same amount, it's mass conservation. Okay, you've got a certain amount of fluid inside the boundary layer, and that's what that continuity equation states. So the amount that flows through here, it's not the exact same amount, I shouldn't say. It's what flows through control volume. For example, if you take a control volume which goes from there down that line, and you go down and go back up and follow the contour of the control volume, you've got a certain amount of fluid going there, a certain amount fluid going in there, and a certain amount going through the upper boundary. And that certain amount going through the upper boundary is v. Okay, it's that y component of the velocity. So mass conservation tells us that the expansion of the boundary layer in the y direction is what governs that fluid moving upward. Okay, so the easiest way to look at it is to look at the derivation. So I won't do that and just say what is the physical reason for V to exist, is to dictate that growth of the boundary layer. At the same time, the momentum that you have in the boundary layer is less than what you would have without, or if there was no boundary layer. If there was no boundary layer, when you integrate 0 to delta, the velocity, if you said the velocity is actually u infinite, you would have a certain transport of momentum. You recognize the real velocity. You multiply by the hypothetical one that would be there without the boundary layer, and you look at the difference to what it actually exists, and that gives you what is called the deficit of momentum due to the boundary layer. The boundary layer contains fluid that moves slower than on the outside. That's why we talk about a deficit in the momentum transport through the boundary layer. That deficit in momentum leads to or changes with space, and the change of it is essentially directly linked to the shear stress. So shear stress is what essentially drives the deficit in momentum, and the change of it leads to a change in deficit. So this is essentially a physical interpretation of all that, but that's not actually what we're interested in. What we do is we first of all start deciding, okay, we have a governing equation, which is an approximate one. Now let's see if we can find a solution that fits that approximate solution. And where you could write it is A0 plus A1 multiplied by that plus A3. Sorry, I'll explain why I moved to A3 straight away, because I'm missing a term here, which is 2 and 2. Okay, so what we're starting to do here is make an assumption about the shape of the variation of the velocity with respect to distance from the plate. We have a non-dimensional definition here. U is expressed as a function of y, but instead of u directly, we look at a non-dimensional form of u is a function of a non-dimensional form of y. We now have an equation which is dimensionally consistent. That is, we've got a non-dimensional term equals to a non-dimensional term, so no issue there. Why do we pick a polynomial? Because if you look at observation from experiment, we know that red curve, which is essentially the variation of u as a function of position along the normal direction, we know it follows a polynomial curve. Okay, we don't know exactly which one yet, so we can leave it as pretty general in this term. Now, what's very useful in this kind of analytical derivation is to first recognize what the boundary conditions are. Boundary conditions is constraints that apply to your variable at different positions in space at the edges of your domain. For example, the velocity of the fluid u is the same as the velocity of the wall at y equals 0. So in this case, if we have a non-moving wall, the velocity u is 0 at y equals 0. At the edge of the boundary layer, we know that the velocity doesn't change anymore. Okay, 99% of the change in velocity is happening inside the boundary layer. And once you get to the edge of the boundary layer, we assume that no change is happening anymore. And that means that u does not change with respect to y. How do you graphically show that? Go back at the top. In theory, it means that the red curve is perpendicular at this stage. Okay, so these two arrows are exactly the same. So the red curve joining them is vertical. It's this condition. At the edge of the boundary layer, also, we assume we don't put 99%, we put the full value. U at the edge is equal to u infinite. And also, if you substitute in the momentum equation, you can show the second derivative there is 0. So how do you use that? Well, you calculate the first derivative of this quantity. It will be a1 times 2a2 y delta times to the power of 1 and so on. And then you impose that condition equal to 0. How do you get 0 there? Well, by having a1 is equal to 0, sorry, du over dy. A1 is the constant. It would have to be a2, that's 0. Okay, so if you just want to illustrate, for example, let's write it down. The dy, starting from the generic function here, it would be, let's write, multiply by 1 over u okay. This is the same as okay. And why did I write it in this way? Because this quantity there is defined now in this way. So if I just make a bit more space so I can see it. The derivative of this with respect to y is 0 plus a1 plus 2a2 times this plus 3a3 to the power of 2. Just a straightforward derivative. Okay. So we have something useful. We know that all of this should be 0. So if you multiply by u infinite, you still have that equal to 0. So all of that should be equal to 0. At 1, or I should say, it's not the whole thing that's equal to 0. It's this. I'll, so it's not this one, it's not it's this one I should write. Okay, so all I'm doing here is I'm evaluating this one at y equal delta. So, yes, I was looking at 0 early on. So at y equal delta, so apologies if there was a confusion, this becomes delta. And this becomes delta. Okay. So we can just remove this here, simplify. We end up with a first condition for effectively 3 of the unknown term. That's 1, and that's 1. So we have a1 plus 2a2 plus a3 should be equal to 0, but we would need to, yeah, so no, that's all fine, that's correct. So this condition gives you one condition for a1, a2, a3. We have 4 unknown in total. That's why we need 4 boundary conditions in order to be able to calculate each one of these a1, a2, a3. Okay, so I'm taking a little bit more time than is strictly needed. So instead, I'm going to shift straight to the solution. That is, this is just take one boundary condition with the other 3 boundary conditions. You get a system of 4 equations for the 4 unknown. And I'm talking about the 4 unknowns, which are A0, A1, and A2. Okay, so 4 unknowns, if you want to write them down, you've A0, A1, A2, and A3. And we find that A0 is equal to 0, A1 is equal to 3 over 2, A2 is equal to 0, and then A3 is equal to 1 over 6. Okay, to give you this, sorry, A3 is equal to minus 1 over 2, apologies. So we do have a solution for u over u infinite, and that's good. That's just from looking at the boundary condition and the assumption of the solution satisfying or following a polynomial curve. That's just an assumption, but it turns out that that assumption allows us to verify the boundary condition, so you're on a good path. The other thing you need to make sure is that they actually satisfy the governing equation themselves. So which one are they? You've got the momentum integral equation, which is important. Okay, you could check first they satisfy continuity. If it doesn't, then you have a problem. But the continuity equation just gives you a condition for the velocity v, and we haven't looked at the velocity v at all. We're just defining u. So essentially, all you need to check under what condition the above functional because we use a function of y over delta to define u, description of satisfies the integral form of the x equation, which is recopied down here. It turns out that if you sub this here and here and here, you can solve it reasonably easily. Okay, so it's not very difficult at all from a mathematical point of view, but you will find a single constraint or a single condition for delta, which is this one. You'll find that the only unknown in your solution will be delta as a function of u infinite, rho, mu, and x. So rho and mu are obviously there. Okay, and we see them appearing here. U infinite is there, so the solution will depend on the free stream velocity. And after that, you end up with your x appearing because of the derivative with respect to x. So when you integrate with respect to x, you end up with x appearing in your solution. Once you have that delta, which is the boundary layer thickness as a function of the Reynolds number, then you can also calculate CF. How do you calculate CF? The coefficient of friction is defined from the shear stress at the wall or at the surface divided by half rho into square. Okay, so that's the definition of the coefficient of friction. Now we also know how to calculate in this two-dimensional problem the shear stress at the wall. It's actually equal to something very similar. So that's why I'm copying and pasting. At y equals 0, because we're looking for the shear stress at the wall. And we mustn't forget to add the dynamic viscosity. So really all we need is to be able to calculate the derivative of u respect to y at y equals 0. So this thing here. Okay. So you end up with the y disappearing, but it's at the function of delta. You see delta there. So if we don't have delta, we can't actually calculate this quantity, but we have it from here. So if you start from there, you will see you end up with okay. So how does that compare with what we have in the table? Reasonably based on the exact same. We've got delta here. We've got delta here, CF here, CF here. So the difference is that it should be 664, and here we have 646. And then we had for delta, we had 5, and we have 4.64. So that's a difference of about, yeah, it's not negligible. It's 92, it's about 8% difference, okay, for the boundary layer thickness. But it's not too bad. And the reason it's not exactly the same as the exact solution is because we satisfy the average integral or momentum equation, that is the one that's been integrated of the boundary layer thickness. So why do I use that as a way to describe the method? Simply because it's easier to describe the step by step, essentially. How do we get there? First thing is if you have the luxury of being able to say, well, we actually know that the velocity of the solution is going to behave in a certain way, that is follow a polynomial curve. You start from a generic one. Then you make sure that the coefficients of your polynomial satisfy the boundary condition that you know from an assessment of the physics. Once you have that, you then attempt to make sure that well, that's what you get after satisfying the boundary condition. Then you substitute this definition into the governing equation to end up with some of the physical term or the terms that have physical meaning, for example, delta, and then you go back to the definition of the coefficient of friction, for example, to get your definition of the coefficient of friction. It's a very similar approach to calculating the Nusselt number. You start again, so Nusselt calculation, or derivations, I should say. Start from functional description of the solution. So in that case, the solution to the thermal problem is what we're talking about, solution for temperature. It's the variable that we want to find and solve for. It's written here again in non-dimensional terms. That is, you've got a non-dimensional term on the left equal to non-dimensional position along the y direction, the wall normal direction. You then use the thermal boundary conditions. I'll copy them now, but I won't get into them. I would ask you to read through them. They are on page 7 of the lecture 5. You essentially have conditions, just to pick one, for example, the temperature at the wall is equal to the temperature of the surface. Okay, so it's all that is equal to 0. They are both equal. The temperature gradient at the edge of the thermal boundary layer is 0, and so on. Okay, so from that, you end up with, again, from the integrated form of the governing equation, with a condition for the thermal boundary layer, that is delta T. Okay, so what's interesting that if you want to write it in a slightly different way, well, no, just we know that in fact this is going to be 1 with the exact solution. So we know that the thermal boundary layer and the hadron boundary layer are almost equal if the Prandtl number is equal to 1. If the Prandtl number is different from 1, then you have a bit of a departure. But that in itself is extremely useful, including in assessing the results that you're going to get with your CFD. That is, a mesh may be suitable for a hydrodynamic condition, but not for a thermal problem if, for example, the thermal boundary layer is much thinner than a hydrodynamic boundary layer. Okay, so if you've got a much smaller region of the flow, which is affected by the plate when it comes to temperature or the thermal effect, than for a hydrodynamic case, then it means you need a lot smaller cells in order to resolve the thermal boundary layer, which can be tricky. So in that case, we make an assumption about the temperature. We can actually find an actual functional description, which I didn't copy, but if you want to see it, it's this one. It's in the lecture notes as well. Once you have that, you can go and look at the definition of, or use the integral form of the energy equation to get your thermal boundary layer thickness. And then by working with the definition of H itself, you can get the Nusselt number. So what's the definition for H? It's given here. Okay. This one you really need to know it. H is defined as minus K. That would be of the fluid. So sometimes you will see F and sometimes you won't see it. That means the conduction coefficient of the fluid, the temperature gradient at the wall, and you non-dimensional, you divide, sorry, not non-dimensionalize, you divide by Ts minus T infinite. So we've got a definition for H in the same way as we had a definition for CF in terms of the velocity gradient here, and now in terms of the temperature gradient. And that's why once you have information about the way temperature change, you can calculate H, and once you've got H, you can calculate the Nusselt number, which is a non-dimensional form of that H coefficient. If you revert back to the summary table here for properties for flow over a flat plate, we see that the thermal boundary layer is different. The exact one, essentially this term is just 1 instead of 0.975. Otherwise, it's almost the same thing. Coefficient of friction we've already done. The Nusselt number, this one is average over the plate. This one is the local value at a position X. And that's for certain conditions. So it's this one that you need to look at, 0.0592. Sorry, Nusselt is here, 0.0296. That's for turbulence. Where am I? I'm looking at the wrong one. Nusselt number is here, sorry. So if you can't see that, Nusselt number is there. We've got 0.33 instead. So I've just demonstrated how to work with governing equation, assumption about profiles in order to derive quantities that are useful to the engineer. These apply only for laminar flow, and you will see that there is a way to derive the exact solution, and I'm not going to cover it. So instead, I'm just going to go back right there at the exact solution, which is derived by solving analytically, that is using calculus, Solution to the boundary layer equation for flow over flat plate. Boundary layer equation for flow over flat plate are given here. So there is a method for solving this, and it gives you this exact solution, which is what you see appearing right here. Okay. So again, just to wrap it up, well, actually, I'll stop now because I've got a call. Thank you.